Hello YouTube! In this video I want to present an argument against scientific realism that hasn't received quite so much attention, but that I think is pretty interesting. So this video will build on some of the points that I raised in a recent video called Science, Knowledge and Complexity, although this video can be viewed in isolation as well. So the argument I want to discuss is what we might call the failure of fit argument. The basic idea of this argument is that there is a mismatch between our language or our representations and the world. Our representations of systems in the world fail to hook up to the world in the kind of way required by traditional realism. Again, as I say, this is something I have discussed in that previous video as well, so you might want to check that out too. Okay, so first of all, what is realism in this context? Well, I do have a series on scientific realism, which you can check out if you are unfamiliar. But essentially, the realist says that scientific theories are attempts to describe a mind-independent reality, and that we are justified in believing that at least some of our best theories are approximately true. The entities and processes described by our best theories really do exist, and they really do behave in the ways specified by those theories. There really are electrons, mitochondria and black holes. The sun really does derive its energy from thermonuclear fusion. Plague really is caused by the bacterium Yersinia pestis, and so on. Furthermore, these truths are objective, independent of us. There are electrons, regardless of what anybody thinks about it. There would have been electrons even if nobody had ever come up with theories about electrons, even if no humans had ever existed at all. This is the sense in which, science discovers facts about a mind-independent world. Okay, so with that said, let's consider the failure of fit argument. Here's an initial statement of the argument from Thomas Kuhn's book, The Road Since Structure. So Kuhn says, evaluation of a statement's truth values is an activity that can be conducted only with a lexicon already in place, and its outcome depends on that lexicon. If, as standard forms of realism suppose, a statement's being true or false depends on whether or not it corresponds to the real world, independent of time, language and culture, then the world itself must be somehow lexicon dependent. Whatever form that takes, it poses problems for a realist perspective, problems that I take to be both genuine and urgent. Kuhn doesn't actually expand on this point here, but so first of all, lexicon. Well, a lexicon is kind of the language of a theory, or perhaps we could think of it as the classification scheme of a theory. So consider, for instance, how the concept planet changed with the shift from Ptolemaic to Copernican astronomy. In the Ptolemaic system, planet referred to any of the wandering stars, right? Any celestial object that moved relative to the fixed stars. So both the sun and the moon counted as planets, while the Earth did not. Under the Copernican system, planet refers to any object that primarily orbits the sun. So the sun was no longer a planet, the Earth was. The Ptolemaic and Copernican systems had different lexicons in this respect. They classified and organised the world in different ways. They grouped different things together. From the Ptolemaic point of view, to say something like planets orbit the sun, that would have just been incoherent. So part of the Copernican revolution involved the development of new concepts which classified things in different ways. And of course, notice that we could actually use the term planet in the Ptolemaic way if we wanted to. There would just be kind of, there would just be sort of no point, right? It's the Copernican concept gives us a much better understanding of astronomical phenomena. Anyway, Kuhn's point is that the traditional realist appears to be committed to the view that, in some sense, our theories speak the language of the world. To give a true objective account of some system is to provide a description of that system that is stated in the system's own terms, or that uses categories that mirror the categories of the system. So again, if we think of the shift from Ptolemaic to Copernican astronomy, well, the Ptolemaic concept of planet fails to capture any genuine kinds in the world. We now know that, the sun, moon and Jupiter, for instance, are all very different kinds of objects that have different relations to the rest of the solar system. By contrast, the modern definition of planet applies to things that do share genuine similarities, even if there is some vagueness in its exact application. Now, truth consists in some sort of relation between a proposition and the world. A correspondence theorist will say that a proposition is true just in case the proposition corresponds to the world, just in case it matches the world in an appropriate way. I mean, as stated, that's obviously just a metaphor, and the metaphor might be developed in various ways, but I mean, it does capture an important intuition, and it's an intuition that, I mean, any theory of truth will need to accommodate. When we evaluate the truth value of a proposition about the world, we do so by, in some sense, comparing the proposition with the world and making sure that they match. When we say verity is at the beach, well, the term verity, that picks out a particular individual. The term the beach picks out a particular place, and then the proposition asserts a relation between them. And we can then examine the world to see if this individual and this place exist, and if so, whether they are related in the appropriate way. Now, truth presupposes a language. You need a language in which you can form statements that have a truth value, and this must involve some set of concepts. So that, you know, there can be no truth completely independent of conceptual schemes, right? Like, without a set of concepts, there's obviously no way of formulating propositions about persons or places or relations or anything else, right? You need to for it to be true that verity is at the beach, there has to be the concept of the beach in order to formulate that proposition in the first place. This is, a fairly trivial point, but Kuhn's idea is that this trivial point has the consequence that if truth involves a relation between statements and the world, then the world itself must have something like our conceptual structure somehow built into it. So there can only be a correspondence or a match between our statements and the world, right, if they share a conceptual structure. So to suppose that there are objective truths, truths that are independent of us, we would have to assume that the world itself has a linguistic or conceptual structure built into it that is then inherited by our representational systems. And again, this point is perhaps somewhat vague, so here's, I'll just give another way of putting the point. This comes from Ron Guerrieri in an article discussing Kuhn. He summarises this idea quite nicely, so I will quote Guerrieri at length. He says, "One should begin by insisting that truth is a relation between a statement and the world. So any talk of truth presupposes a language. Truths independent of human conceptual schemes would have to be understood as related to the world's own language, so to speak. That idea, as Nietzsche points out, made sense assuming the Christian God who spoke the world into existence. The world's language is God's language. On Nietzsche's telling, Enlightenment philosophers killed God, but failed to realise that meant eliminating God's truths as well. Contemporary philosophers, including most scientific realists, are making the same mistake. One would have to presume that discovering truths about the world required first coming up with the right set of concepts, in effect, discovering the language that a Christian God would have used. Given that human languages are historically evolving representational systems, and that the world is incredibly complex, that seems most unlikely, even if not logically impossible." Guerrieri makes the same point about laws. Originally, Guerrieri says talk of laws was drawn from Christian theology. Laws of nature were thought of as being literal laws, laid down by a lawgiver. The world is governed by laws of nature in that it follows God's commands. So, here again, we have this notion of the world being spoken into existence by God. Over time, of course, these explicit theological notions dropped out of our understanding of science, but scientists and philosophers continue to think of phenomena as being governed by laws. But now it's much less obvious how to actually explicate the idea of things being governed by laws, right? When, the notion of law is just a metaphor and there is no lawgiver. Okay, so, hopefully this gives you a sense of what the challenge is. It is, I think, a little bit difficult to actually state this challenge in a way that is clear and precise and that doesn't rest on perhaps questionable metaphors. So, the question for the realist is, could there be a language of the world? And if so, could our theories speak it? So, I mean, Kuhn and Guerrieri find the idea of a lexicon-dependent world vague or perhaps incoherent, but there are reasons to take this seriously. So let's consider what a realist might say in defence. I mean, there are, broadly speaking, two ways to approach Kuhn's challenge. First, the realist might grant that we cannot yet specify exactly what the language of nature is, but then she can give reasons for optimism that our representations do match the world in the right kind of way. Like, even if we can't say exactly, even if we can't give a specification of what exactly the language of nature is, we can still be optimistic that there is the right kind of match. And then the second way of approaching Kuhn's challenge is to actually try to give a specific proposal and say, this is the language of nature. Okay, so let's begin by considering reasons for optimism. First, there is the denial response. So one option for the realist is simply to deny that there is any challenge here in the first place. The idea is, okay, look, all that's ever been required for realism is that we are justified in believing that at least some of our best theories are true. The realist simply does not need to make any further commitments. In particular, the realist doesn't need to adopt any controversial positions with respect to, metaphysics or theories of truth or whatever. Like, as long as you accept that, yep, there are electrons, and the reason why we're justified in believing in electrons is because of the successes of our best theories, well, you're a realist. That's it. So this is essentially the response given by Alan Musgrave to Arthur Fine's natural ontological attitude. So I have a video on the natural ontological attitude in my scientific realism series, but just to give a brief intro here, Fine attempted to carve a middle path between realism and anti-realism, and he argued that we can identify a core position shared by realists and anti-realists. As Fine sees it, the core position is simply that well-confirmed theoretical claims are true, on par with the homely truths that we all accept about, the things that we perceive with the senses, cars and mountains and oceans and so on. So all parties to the realism debate, according to Fine, accept that there are electrons and that contemporary physical theory is what justifies this. So just as we all basically trust the evidence of our senses, we all basically trust the results of science. Then what distinguishes realists and anti-realists is that they each add some controversial philosophical claims to this core position. The realist may adopt a correspondence theory of truth, treating truth as a matter of correspondence to a mind-independent world, while the anti-realist may adopt, a verificationist theory of truth and say that truth just consists in, like the method of verification or something along those lines. Fine's natural ontological attitude, by contrast, simply accepts the core position and nothing more. We need not enter into any metaphysical debates, we can just trust the results of science. That's enough. So Musgrave, and many others for that matter, object that Fine has just misunderstood the debate between realists and anti-realists, that actually the debate between realists and anti-realists is precisely a debate about whether we are justified in taking our best theories to be true. Musgrave points out, there are actually lots of anti-realists who do not treat the homely truths about observables and then theoretical claims about unobservables as being on a par. So they will reject what Fine calls the core position. Indeed, for Musgrave, the core position is all you need to be a realist. Then anti-realists like Bas van Frassen will come along and say, no, the aim of science is just truth about observable phenomena. No need to believe in anything unobservable. So they're not treating homely truths and theoretical claims as being on par. So Musgrave's point is, all you need to be a realist is the core position, right? The core position that we can trust the results of science. Well, along the same lines, I imagine that Musgrave would not be moved by the Kuhnian failure of fit argument. He would say, look, realists are not committed to the view that truth consists in correspondence between theories and the world. They're not committed to the view that there is a language of the world for our theories to match, or anything along those lines. So, this Kuhnian argument just assumes a kind of straw man of realism. Now, I think that Musgrave is half right. So what he's right about is that there are plenty of anti-realists who reject the core position. There are plenty of anti-realists who deny that we're justified in taking claims about unobservables to be true, and who deny that observables and unobservables are on a par. Indeed, these brands of anti-realism are probably the most influential in contemporary philosophy of science. So yes, Fine is wrong, I think, in supposing that his core position is shared by all parties. But Musgrave is overlooking other forms of anti-realism, particularly those in the social constructivist tradition. According to social constructivists, scientists do not simply discover pre-existing facts, rather facts are in some sense literally constituted by the activity of scientists. Facts are socially constructed. We make the facts. So, I mean, this can sound a little bit crazy, but if this is not a view that you have, I mean, actually, I suppose, you know, social constructivism is just one of those phrases that's sort of in the air, you know. A lot of people, I think they know what it is. But if you want a good, well, hopefully a good introduction to one type of social constructivism, because there are many types, but one type of social constructivism, you might want to check out my videos on Nelson Goodman's world making, which I made quite recently, a couple of months ago. Goodman is a pretty hardcore constructivist, and yeah, I give an exposition of his view there. So yeah, but basically the constructivist will say that yes, in some sense we make the facts. Now, social constructivists are happy to grant that various scientific claims are true, that we are justified in believing them to be true, that we know them to be true. They might even say that they are true of the external world. Many social constructivists will also treat the everyday homely truths and the scientific truths as on a par, because they will view both as being products of social construction. I mean, this was certainly Goodman's view, right? For Goodman, like we literally make, so we make the facts about cars and oceans and mountains and other things that we observe. So in that sense, they accept the core position. But for the social constructivists, you know, truth, knowledge, facts, these are products of social negotiation. They're not objective, mind independent. So, you know, what distinguishes social constructivism from realism is that they each add a different account of truth to the core position. Here's an example from Derek Turner's book, Making Prehistory, which hopefully will make this absolutely clear. Suppose we find a set of tracks in the snow and we propose the following hypothesis. A deer passed this way not long ago. And then let's say that we accumulate a great deal of evidence for this hypothesis. Maybe we find lots of deer droppings nearby. Then we discover that the area has a high deer population. Then closer inspection of the tracks reveals other types of patterns known to be connected with deer. Then maybe we do some sort of DNA analysis and find deer DNA, and so on. Okay, then, both realists and constructivists will accept that H is true. That's the core position. And I mean, it also seems like H is going to be a homely truth, right? So we can put aside questions about the justification of theoretical posits beyond the observable. So what realists add to H will be something like this. A deer passed this way not long ago, and this occurred independently of the mental, or and this occurred independently of any kind of social activity or social negotiation. For the realist, the fact that a deer passed this way not long ago, that's a fact about the world that is discovered through our investigation. It is independent of us. The constructivist will add something like this. A deer passed this way not long ago, and this was dependent in one way or another on our thoughts now. Okay, we might quibble over this characterization of social constructivism. I guess constructivists might object that, you know, actually their position should be elaborated in some other way, but, you know, this is only illustrative. Constructivists are committed to something like HC. And in any case, the point is, if realists are only committed to the core position and nothing more, then they have no way of ruling out HC and similar claims, right? And I mean, obviously, a realist is going to want to rule out HC, right? Scientific realists would not be happy with that position. So, you know, in order to understand the debate between realists on the one hand and then, you know, constructivists, verificationists, idealists and so on the other, we do need to go beyond the core position. We need to attribute more than just the core position to realists. What then does traditional realism involve? Well, at the very least, I mean, realists assert not simply that our best theories are true, but that our best theories are true of a mind-independent world. Furthermore, truth itself, right, the truth must be something that is independent of us. It is true that there are electrons, and this would remain true even if nobody believed that there were electrons, or even if nobody existed in the first place. Like, it was true that there were electrons even before any humans ever arose, right? Even before humans evolved. Furthermore, truth is transcendent in that there may be truths such that it is, in principle, impossible for us to know them, right? There are truths about, whether or not there is extraterrestrial life in galaxies that are outside the observable universe that we will never be able to detect. So, this point is important, right? What makes particular propositions true is not, say, our available methods of verification, is not processes of social negotiation. Rather, it's how those propositions relate to the mind-independent world. And that's not up to us. So in order for H to be true, it has to be the case that Dia picks out some object in the world, and this object must have done particular things. Now, obviously, we decide what the meaning of the term Dia is, but the realist will say, given that the term has a particular meaning, right, we have no control over whether or not this term has a referent, nor do we have any control over what precisely the referent is. I don't think this is at all controversial as a characterization of the commitments of traditional realism, but with all of this in place, it looks like the Kuhnian has enough to forward the failure of fit argument. So, yeah, denial is not a response to the failure of fit argument. It is simply a refusal to engage with it, and I guess that's fine. You don't have to engage with these positions, but there is a distinction between realists and anti-realists who accept the core position, and the failure of fit argument is relevant to it. Okay then, so that perhaps is not so convincing as a reason for optimism. A second reason for optimism is what I'm calling the argument from evolution. So, for Kuhn and Guerri, there is this mystery at the heart of traditional realism. The mystery is in the idea that the theoretical lexicon corresponds to the world. I mean, clearly, right, languages and lexicons are constructed by humans. So how could it be the case that a language or a lexicon is built into the world itself? But to this, the realist might say, well, look, given that humans evolved within the world, and given that the capacity for mental representation evolved presumably to represent the world, there's no mystery at all about why there would be a correspondence. There's good reason to expect a match between our representations and the world because our conceptual capacities evolved to match it, evolved to allow such a match. I mean, so if you consider this in terms of the theological view, right, like God spoke the world into existence, and he also spoke our minds into existence. Presumably, when he did this, he intended for us to be able to discover truths about the world. Well, it's no surprise then that our language would match the language of the world, right? The capacity of our mental representations to appropriately match the world is a kind of adaptation, and on the theological view, that's explained by God bringing about both sides of the correspondence. Now, today, of course, we can explain adaptation by appealing to evolutionary theory, and why shouldn't we just take the same sort of line here, right? Like the world has a conceptual structure, and yeah, we evolved to match it. I mean, another way of putting the point is, like, Kuhn and Guerri begin by thinking about theories and language, and then they wonder, well, how could the world itself have these relevant language-like features? After all, language is a human tool. In projecting the properties of language onto the world, we seem to be engaging in this bizarre kind of anthropomorphism. But the realist might suggest, we have the representational tools that we do because of the way the world is. If the world had not been lexicon-dependent, as Kuhn puts it, then any organisms within it would have evolved different representational tools. Now, of course, this response doesn't tell us exactly what the lexicon dependence of the world is supposed to amount to, but as I've noted, the argument from evolution, this is an argument for optimism, that that there is an appropriate match without spelling out exactly what that match consists in. Okay, so one objection to this argument is that it's simply question begging. So it might be said, this argument assumes that all humans have occupied the same world, that all of humanity evolved in the same environment in the relevant respects. Because, if our ancestors evolved in worlds with different lexicons, then there would be no reason to assume that the lexicon of our language matches the lexicon of our world. But now, consider this from a social constructivist point of view. I mean, if facts are socially constructed, then the facts, and presumably also, the lexicon of the world, would have been different in the past, right? When people had different theories, different perspectives. Somebody like Nelson Goodman would seem to be committed to saying that our ancestors quite literally lived in different worlds. If their representational tools developed for those worlds, and those tools are being passed down to us, then there's no reason to expect correspondence with our world. Now, I don't think this is a particularly convincing objection. It seems to me that what the realist needs here is just coherence by her own lights. Remember that the Kuhnian failure of fit argument is presented as an argument against realism. The claim is the realist is relying on this notion of correspondence between representation and world that doesn't make any sense. The argument from evolution is supposed to give the realist a license for optimism. So it's supposed to show that, yeah, we can, at least assuming realism is correct, we can understand how the correspondence obtains. Now, of course, if you begin by assuming an anti-realist position, such as social constructivism, then, sure, we may no longer be able to say that all humans evolved in the same world. But we can't begin by assuming that, because the Kuhnian argument is supposed to establish that, right? The Kuhnian argument is supposed to be an argument for that sort of position. It's supposed to be an argument for anti-realism. So yeah, I think that the realist, it seems to me, can reasonably say that her position is coherent by her own lights, and that's all that is required, right? The point is actually, from a realist point of view at least, the idea of correspondence between theory and world does make sense, and if you look at it from the point of view of evolution, you can understand why. However, there are problems for the argument from evolution. Most seriously, our best science appears to reveal that we've actually been endowed with representational capacities that systematically generate false representations of the world. It's actually understandable why this would be so. After all, what matters for evolution is not true representation, but merely useful representation, where utility is a matter of survival and reproduction. Of course, organisms must respond appropriately to the world, right? But appropriate responses do not need to be mediated by representation of any kind, let alone by representation that corresponds to the world. So in fact, we do find plenty of cases where we have false or distorted representation. Consider, for instance, folk physics. Folk physics is our untrained everyday understanding of physics, which involves significant simplification and distortion of physical phenomena. Folk physics, for example, includes the assumption of absolute simultaneity, which is a reasonable assumption given that relativistic effects are negligible in everyday life, but that's false. Folk physics also contains distortions about matters that are relatively easily observable. Michael McCloskey reports some interesting studies in his article, Naive Theories of Motion. McCloskey presented subjects with various problems about motion. In one problem, they are told that a person has a ball attached to a string and is spinning the ball above their head so that it follows a circular path, as shown in the diagram on the left here. Now, eventually the string breaks and the ball flies off, and subjects were asked to describe the path of the ball after the break. Now, rather than depict the ball flying in a straight line in the correct answer, which is shown in the middle diagram, many of the subjects assumed that the ball would follow a curved path which would gradually straighten out, right, as though the ball had been imparted with some sort of intrinsic circular motion that would gradually be lost. That's wrong. Now, McCloskey suggests then that folk physics assumes a kind of impetus theory of motion. Or consider visual perception, which seems to present objects with intrinsic colour properties. Well, there are powerful reasons to think that colour properties do not inhere in objects intrinsically, but are at best a product of interaction between organism and environment. There doesn't seem to be anything that unifies all of the things that appear red to us. Red might be produced by monochromatic light source, say emitting light of 700 nanometers, or it might be produced by a light source emitting various wavelengths, or it might be the product of scattering of light, as in the red sky, or it might be light reflected off a surface, and there are a host of different kinds of surfaces that will appear red. In addition, whether or not an object appears red depends on the colours around it. It depends on the conditions of like illumination, you know, what type of light the object is illuminated under. So, you know, it's at least questionable, right, that colour actually exists in the world mind independently. I mean, certainly, right, the idea that objects just have intrinsic colour properties on their surfaces, which is how perception seems to present objects, well, that seems like it's probably not true. So, in a wide range of cases, it appears that there is selective pressure for representation that abstracts, distorts, and simplifies. So the claim will be, well, if the world has a lexicon, there is reason to think that it is not our lexicon. The fact that humans evolved in the world just doesn't help. Okay, well, I know of no other general argument for optimism, so I will now turn to specific proposals for what the language of nature could be. The obvious answer here is that is to appeal to natural kinds. So one important thing that scientific theories do is they classify things in the world. Think of the periodic table, which provides a classification of the elements, or biological taxonomies that classify species. A realist will say that the world itself is divided into kinds. So some of our classification schemes are arbitrary or artificial or dependent on our interests, but some of our classification schemes track the genuine order of the world. They mirror the natural kinds, or they carve nature at its joints. So take on the one hand our classification of objects into different colour groups. We can order objects based on their colour under a given illumination, you know, red, orange, yellow, etc. But this classification, as we noted just a minute ago, well, this arguably tells us more about ourselves than it does about the world, because on investigation it turns out that red objects have nothing in particular in common except for the fact that they appear red to us. Many red objects will have surfaces that resemble much more closely the surfaces of blue objects than other red objects. If an organism with a different visual system were to look at our red objects, it would see an arbitrary collection of items. I mean, in addition, it turns out that even among humans, there's no unique way of ordering colours. Different societies classify colours in different ways. So in many languages, there is no distinction between blue and green. In some languages, they treat what we call dark blue and light blue as totally distinct colours. So, you know, colour classification is largely a matter of convention. Compare this to the classification of elements found in the periodic table: hydrogen, helium, lithium, and so on. Well, in this case, there are very clear and sharp distinctions between the different kinds. All of the atoms of gold are alike, all contain 79 protons, and they're all different from all the atoms of mercury. They're sharply different from all the atoms of mercury, which contain 80 protons. Knowing that something is composed of a particular kind of element will allow us to infer many of its other properties, because an atom's place in the periodic table will determine how it interacts with other things. We might expect that an advanced alien civilization with a completely different biology and completely different interests from us would surely also have come up with the periodic table, you know, at least if they engaged in scientific investigation for long enough. The periodic table mirrors the joints of nature. So in this kind of view, the language of nature is a language of kinds, and our scientific classification schemes match the natural kinds. Now, I mean, this is probably the most obvious response to the Kuhnian, but I'm not going to look at any of the arguments against it here, just because I've already got a video specifically on this topic, which I made quite recently. It's called Classification and Kinds, an Antirealist View, and I'll link it below. You might also want to check out my video on natural kinds essentialism. And again, just to be clear, I'm going to skip over this, not because it's unimportant, but just because I've like literally already just made a video on this exact topic, and it seems kind of pointless to, you know, repeat that material here. So with that said, I'm going to move on. So let's assume that for reasons stated elsewhere, we do not favour the appeal to natural kinds. What else might the language of nature be? Well, perhaps the most famous instance of this metaphor of the language of nature is Galileo's comment that the book of nature is written in the language of mathematics. And I think this kind of sentiment is probably shared among many other scientists, right? What science reveals about the world are its mathematical properties. And when we understand the mathematical properties of a system, we understand the system in its own terms. Now, while there seems to be something rather odd in the notion that the terms and categories of a natural language could somehow be built into the world, the notion that the world instantiates mathematical properties is, I mean, far less mysterious, at least at first sight. I mean, part of the reason for this, I suppose, is just, like, we all know that natural languages are clearly a matter of human convention, right? Like, we've clearly created natural languages for our purposes, and, you know, we have different concepts depending on different interests, whereas mathematics is universal, or at least it arguably seems to be. I mean, it's also quite clear that the mathematization of nature was a key step in the scientific revolution. The application of mathematics massively accelerated scientific development. Now, in its contemporary form, mathematization is associated with structuralism. Structuralists hold that inquiry into some domain can reveal only the structural properties of that domain, where structural properties are mathematical properties. So, well, I guess here's a simple example to sort of illustrate this idea. This diagram shows the behavior of light. This shows what happens when light travels from one medium to another. You have the light being reflected off to the left and then refracted to the right. There's a very simple law for reflection. The angle of incidence equals the angle of reflection, assuming the surface is smooth. As for the angle of refraction, that depends on the medium through which the light travels, and that's given by Snell's law. This tells us that the refractive index, n1, of the first medium times the sine of the angle of incidence, or alpha, is equal to the refractive index, n2, of the second medium times the sine of the angle of refraction, or beta. If we know the index of the first and second, the refractive index of the first and second medium, and we know the angle of incidence, then we can work out the angle of refraction. Now, the details of all of this are not important. For our purposes, the thing to note is this. Snell's law has been retained over several centuries, even though our views about the nature of light have undergone significant revisions. For a long time, many people held the corpuscular theory of light, believing that light was composed of streams of particles. This was then displaced by the wave theory, in which light was thought to consist of disturbances in a subtle material substance known as the luminiferous ether. Today we understand light as a type of electromagnetic radiation, and we have eliminated the ether, though photons still behave as waves and exhibit wave-particle duality. So we've had these significant changes in our understanding of the ontology of light, but the mathematical description of the behaviour of light has survived through these theoretical changes. And I mean, this is just one example, but there are many other equations describing the behaviour of light that have survived these ontological shifts. So this hopefully gives you an intuitive sense of the kind of structuralist account, right? Like what we learn are the mathematical properties, but we do need to give a more general definition of structure, right? Like, what exactly do we discover when we discover the structure of a system? So Roman Frigg and Ioannis Votsis, in their article "Everything You Always Wanted to Know About Structural Realism," define structure in set theoretic terms as follows. So they say, a structure S consists of first, a non-empty set U of objects which form the domain of the structure, and second, a non-empty indexed set R, i.e. an ordered list of relations on U where R can also contain one-place relations, i.e. monadic properties. Okay, let's take two structures, so S1 and S2. We would say that these have the same structure just in case they're isomorphic, which is to say that every element in U1, so to every element in U1, some element in U2 corresponds, and when two elements in U1 bear the relation R1, the corresponding elements in U2 bear the relation R2, and vice versa. So, in other words, S1 and S2 have the same structure just in case there's a one-to-one mapping from the objects and relations in S1 to the objects and relations in S2. Now that's all rather abstract, so here's a specific illustration. Suppose that S1 is a set of 10 balls, each of different sizes, and S2 is a set of 10 sticks, each of different lengths. We can order the balls by the relation larger than, and we can order the sticks by the relation longer than. We can then define a mapping from each ball to each stick, such that for any two balls where one is larger than the other, there are two sticks where one is longer than the other. We can relate each ball to each stick, so that for like the larger ball, the corresponding stick will be longer than the other stick. So we'd say then the set of balls has the same structure as the set of sticks. And what we've done here is we've abstracted away from the nature of the objects and relations. From a structural point of view, it is irrelevant that the objects are balls and sticks and that the relations are larger than and longer than. According to the structuralist, theories present mathematical structures, and these can then be mapped to the mathematical structures instantiated in the world. In this sense, there is literally a correspondence between our theories and the world. Scientists speak the language of nature by mathematizing their theories, and this is known as the mapping account. So in the description of structure given by Frigg and Votsis above, just think of S1 as a theoretical structure and S2 as a structure instantiated by a target system in the world, with the mapping from S1 to S2. One of the things that is appealing about structuralism here is that from a structuralist point of view, the nature of the objects that instantiate the structure is irrelevant. So, a set of balls and a set of sticks can have the same structure. In the same way, then, a system in the world and a theory or model created by scientists can have the same structure too. So this is how we make sense of the idea of a language of nature, right? Nature instantiates mathematical structures, and then models and theories can be developed that instantiate literally the same structure. So, does this work as a response to the Kuhnian? Well, so first of all, I do want to be clear. The goal here is not to criticize structuralist accounts of science, right? The question is simply whether the appeal to mathematical structures provides a plausible solution to the Kuhnian challenge, right? Can we take mathematics to be the language of nature? Well, there are some problems here. So first of all, note that the physical world is not in any obvious way a mathematical structure because mathematical structures are abstract. They have no spatiotemporal properties and they do not enter into causal interactions. Now, when I was describing structuralism, I spoke of target systems instantiating mathematical structures. But the relation between physical systems and mathematics is really controversial. And part of the problem here is that there isn't any consensus on the ontology of mathematics in the first place. So we're inquiring about a relation between the physical world and, well, what? Right? What exactly is the second thing here? Right? We need a relation between the physical world and the mathematics, but what is the mathematics? Different philosophers have very different accounts of what mathematical structures are. Indeed, according to many positions in philosophy of mathematics, so according to fictionalists, according to eliminative structuralists, according to Meinongians, mathematical propositions purport to describe abstract structures, but no such entities exist, right? Mathematical structures do not actually exist. On these views, mathematics is a useful tool for representing physical systems, but to talk of physical systems instantiating mathematical properties, that's merely a manner of speaking. There are no mathematical structures, so there is no relation between them and the world, whether it be identity, instantiation, mapping, or whatever. Now, for most purposes in philosophy of science, you can put these kinds of debates to one side. But I think, for anybody proposing mathematization as a solution to the Kuhnian challenge, this kind of issue can't be avoided, because, the issue here is like a claim about the world itself, right? We want to know what the world itself is like. So we're not just saying, that representation involves talking in terms of mathematical structures. We're saying mathematical structures are part of the world. And, there are going to be a lot of views in philosophy of mathematics that reject that. The second problem, as James Guyon and Roman Frigg point out in their article, Mathematics is Not the Only Language in the Book of Nature, is that the structure of any given target system is indeterminate, in that any system can sustain a host of different structures. So, as we noted, a structure is instantiated by a domain of objects plus relations on those objects. So, in order to identify the structure of some system, we need to identify there are certain objects and certain relations. Now, as we noted, we don't need to identify anything about the nature of those objects and relations. It doesn't matter whether we're dealing with balls or sticks, or larger than or longer than. But the number of objects does make a difference. If U1 contains 10 objects and U2 contains 11 objects, then there won't be a one-to-one mapping from the elements of U1 to the elements of U2. So S1 and S2 would not have the same structure. With that said, consider a biological population, for instance. Well, in principle, the world itself doesn't compel any particular way of carving up this population, right? Like when we ask what are the objects here, the world itself doesn't compel any particular way of dividing this into objects. We could take the objects to be the individual organisms, or we could take pairs of individual organisms as the relevant objects, or we could count just the teeth of organisms as objects, or we could count the left side and right side of organisms as different objects, or we could take the molecules composing the population as the objects. Now, of course, many of these ways of dividing the population will seem highly artificial, but there's no reason from the point of view of determining the mathematical structure why any of these would be ruled out. In addition, it turns out that in practice, biologists do appeal to a host of different individuality concepts. So, do the human gut flora count as part of the human individual, right? Or do they count as separate individuals that exist symbiotically with the human individual? Well, those types of questions, it turns out, are kind of hard to answer. I have a couple of videos on biological individuality if you're interested in more in this, but suffice it to say, there are a host of different cases throughout the biosphere that will put pressure on any given definition of biological individuality. There are something like, I think, 40 different definitions of biological individuality, of what makes something a biological individual, available in the literature. So, the members of the biological population are indeterminate in this sense. Even once we specify members of the population, we can consider a whole host of different relations. We can consider the ancestor-descendant relations and group them according to according to relations of being ancestor and descendant. Or we can group them according to size, or we can group them according to number of cells, or according to their proximity to the sun. We could group them according to colour. There's no way from a purely mathematical point of view to rule out any of these arbitrary groupings, and all of these will lead to a different structure for the population. So what Guyon and Frigg say is there's no such thing as the structure of a population. Many structures can be defined depending on how we carve up the population and on what features we're interested in. And obviously the same points can be applied to any other target system you like. So Guyon and Frigg propose that the application of mathematics to a target system requires the construction of what they call structure-generating descriptions of that system. A structure-generating description is a description that specifies the relevant objects, properties, and relations of the target system. The scientist must first select those aspects of the target that she's interested in and divide up the system, carve up the system in a particular way. for a biological population, the scientist will first specify the members of that population, guided by some individuality concept, and then she will specify certain relations, such as relations of reproduction or parent-offspring, and so on. So then we get a description of the population, and this is a description in physical terms. It's not a specification of mathematical structure. Like you'll talk about rabbits, and this rabbit is the parent of that rabbit, and so on. The next step is to schematize the description, which involves abstracting from the specific natures of the objects and relations given in the description. So terms referring to biological organisms will be replaced with terms referring to objects, just objects in the abstract. If the description talks of 5 rabbits and picks out a particular rabbit as the first rabbit, another rabbit as the second rabbit, then the new schematized description will remove reference to rabbits and talk only of objects. Then terms defining relations are replaced with terms that specify only the extensions of those relations. So parent of, for instance, will be replaced with a term that tells us which objects the relation holds between, but nothing more. So we'd move from a claim like rabbit A is the parent of rabbit B to like O1R02. It just specifies abstract object and relation. And at this point we have a description of a structure. This structure can then be mapped to a mathematical structure specified by a theory or model. The application of mathematics then involves moving from a physical description, PD, to an abstract structural description, SD. SD can be mapped to a mathematical structure. But crucially, the crucial point here is we cannot at any point eliminate PD, because PD, the physical description, this plays an essential role in coordinating the mathematics to the target. If you don't have PD, then all you have are abstract structures which can no longer be taken to apply to anything. You've literally just you're just playing around with abstract mathematics at this point. So Guyan and Frigg say, a structure applies to a target always only relative to a structure generating description. But structure generating descriptions are given in natural languages, and so now we are back to the question of the lexicon dependence of the world. In many ways I think this is kind of an obvious point, right? Like, it's an obvious point that mathematical formalism in itself says nothing about the world. A person can do mathematics and explore mathematical systems just for the sake of exploring a mathematical system, right, without thinking of how it relates to anything else. So for a mathematical structure to have an empirical application, it has to be interpreted. And the point here is that this interpretation cannot be given in purely mathematical terms. We have to identify aspects of the structure with aspects of the world. We need a mapping from the model to the target system in the world. And the defender of the mathematization response might be tempted to say, well, what's happening here is we're just identifying the structure of the model with the structure of the world. But the question is, well, okay, but how exactly are we specifying the structure of the world? If that's supposed to be a purely mathematical structure without physical interpretation, then we're no longer talking about the world. We'd just be presenting two mathematical structures. There is a difference between presenting a structure for its own sake and presenting a structure as the structure of some worldly system. And the claim will be that mathematics alone is not sufficient for presenting a structure as the structure of some worldly system. In order to present a structure as the structure of a system, right, we need a physical description of that system that coordinates the structure to the system. That is the claim that Guyan and Frigg make, at least. So I've framed these points in terms of the structuralist approach, but we might think, well, okay, couldn't the defender of mathematization think of mathematization in different terms so as to avoid this problem? I think this is doubtful for a couple of reasons. So, the main reason is just that I think that this problem of coordinating, mathematical structure to the world, I think that problem is going to arise for any plausible conception of mathematical properties, because what's really driving this problem is that the mathematical objects and relations are abstract. And the real difficulty here is the question of how we coordinate abstracts with physical systems. A second problem, though, is that the structuralist approach has a really significant virtue, which is that it provides us with a clear and well-developed account of what exactly mathematical language is, and which is applicable to mathematical models across the board. Many different mathematical representations are available for what the structuralist would treat as the same structure. So if we abandon the structuralist approach, we only increase the abundance of mathematical representations of any given target system. Consider Galileo's mathematization of freefall. Today, relations that are represented algebraically were originally presented by Galileo using geometrical representations. Galileo understood freefall in geometrical terms, in terms of lines, points, proportions. Indeed, the full quote, which I noted as inspiration for mathematization, is that the book of nature is, I quote, written in mathematical language, and its characters are triangles, circles, and other geometric figures. The algebraic representation and the geometrical representation are equally accurate, though, today we take algebraic representations have greater pragmatic virtues. But, we then have this question of, okay, well, which is the language of nature, right? I mean, is it somehow like the algebra? Is it the geometry? Is it something else? The structuralist avoids this problem because both can be representations of the same structure. Okay, there is one final difficulty for the mathematization response. And again, this applies whether you're a structuralist or whatever kind of view you take of mathematical properties. This is that the mathematical structures used in science often don't even prima facie map to real-world systems, but only to idealized models of those systems. So take the model of the simple pendulum. This idealized model assumes that there is no friction or air resistance, that the bob is a point mass, that the cord on which the bob swings is massless and perfectly rigid, that the gravitational field is perfectly uniform, and so on. So we have a model, right, which, I mean, completely, like, obviously there's no real pendulum that is anything like this, right? We have idealized in many, many ways. The differential equation that describes the motion of the ideal simple pendulum is not true for the motion of any real pendulum. Now, obviously, some of the idealizations in the model pendulum can be removed. We can remove idealizations so that we account for friction, say. But this will increase the complexity and it will increase the accuracy of the equations describing the motion, but it's far beyond our computational capacities to remove all idealizations. There's always going to be some idealization involved in any model of a pendulum. In practice, then, mathematical structure is often not taken to map directly to the world itself. The mathematization of science has proceeded not through the attempt to describe the world in itself just directly, but instead it's proceeded via the introduction of idealizing assumptions. So we're not simply using mathematics to describe the world. And I mean, obviously there's much to be said about why exactly idealizations are useful and how it is that we can use falsehoods to learn truths about the world, and lots of interesting questions there. The point in this context is, well, I guess it's simply this. The fact that mathematical structures are useful devices for scientific representation does not show that mathematical structures objectively correspond to the world, because there are a host of cases, just pick any idealized mathematical model, a host of cases in which we know that these structures are useful but do not correspond. At least they don't correspond in any obvious way, right? Like the equation describing the motion of a idealized simple pendulum does not in any obvious way match the motion of a real pendulum. So in this respect, mathematical description seems to exhibit much the same problem as natural language description. Of course, you can always say, well, a real pendulum could, in principle, be described in perfect detail mathematically. There's some equation which truly describes its behavior, even if we could never discover this. But, similarly, we can say, there's a natural language description of the pendulum that is perfectly detailed and accurate. None of this is to say that structuralism in general, or structural realism or any other given view like that is mistaken. The question is just whether mathematization and structuralism can support this idea of a language of nature, a mind-independent correspondence between our theories and the world. And there are some reasons for skepticism on this point. So those were some challenges to that way of conceiving of the language of nature. And, you know, I think that is enough for today. I hope you found that interesting. Goodbye.